Hello, welcome to this module on basics of serial communication for the substation engineer. My name is Alin Anto and I am an assistant manager in at Hitiur substation SR2. So in this course, we'll cover about basics of serial communication that is used in a substation like UART, RS-232, RS-485. You might have heard of these terms. We'll also cover the Modbus RTU protocol in detail. We'll also touch on the network models that are used in Ethernet and will deviate into the Ethernet standard. We'll only we'll only cover the introduction to Ethernet because the higher levels or integrities of Ethernet are not in this scope of this course. So the target audience is any engineer or technician who works in the IT or OT network. They can get a hang of all the serial communication protocols, how the wiring is done, what is the logic behind each connection that they're making. They can get a basic knowledge of the network model, OSI network model, and introduction to Ethernet. What are the various factors to keep in mind when you're making Ethernet wiring or Ethernet network? And since this is a beginner level course, you're not going into the details of anything. There is no prior coding knowledge or no prior knowledge required. If you have a familiarity with these devices or these terms, that would help. So at the end of this course, hopefully you will have a basic understanding of serial communication that is being used in a substation, and you will be able to do hands-on work on your own. You will be able to make all the wiring, understand the network on your own. So the first module is introduction, and in this basically what we are going to cover is the difference between serial communication and parallel communication. We'll start with that, and then we'll move on to modes of serial communication like asynchronous, synchronous, and the integrities of that. So first of all, serial communication and parallel communication. So nowadays, when you talk about communication, ultimately you're talking about digital communication because data is nowadays represented digitally in almost all devices. So when talk about digital communication, we have to talk about bits and bytes first. So data is ultimately stored in a device as bits and bytes. So a byte is a collection of 8 bits and a collection of bytes is called a word. So each computer device or each digital device is having a word length. For example, a 32-bit device has 4 bytes as word length. Means 4 8 bytes form a 32-bit word. And a 64-bit computer has a word size of 8 bytes. So that is, you don't have to worry about the term word size, but just keep in mind that data is ultimately represented as bits and bytes in a digital device. So by communication, what you mean is getting this byte across from one device to another. So you can do that in two fashions. Because a byte is a collection of 8 bits, you can send all the 8 bits at once. Or for example, if your computer is having 32-bit architecture, you can send all the 32 bits at one to the other device. So in such a scenario, you need, if you're sending all the bits at once, you need that many channels for doing. So for example, in this figure, you can see you're sending 8 bits from 0 to 7 at once to the receiver. So you are using 8 physically separate channels to send the data across, and you're sending it one at once. All the 8 bits are getting transferred at once. Whereas in a serial interface, you're sending it one by one. You're first sending the 0th bit, followed by the first bit, and sequentially you're sending 7 bits. So what happens is data is transferred in clock cycles. You might all be familiar with what is a clock cycle. I'll explain about clock cycle in detail later in this video. But now, for example, it takes one clock cycle to send a bit, suppose. So in a parallel fashion, what will happen is you're sending all the bits at once. You just take one clock cycle and your entire 8 bit or 1 byte is transferred at once at one clock cycle. But in a serial interface, you need 8 clock cycles to send the 8 bytes. So you're having, suppose you're having an 8 bit data, you need 8 times more clock cycles. And if you're having a 32-bit data, you need 32 more clock cycles to send the same data. So ultimately, if you're thinking serial communication is a bit slower, naturally you might be getting that feeling that serial communication is slow. Why are you using serial communication at all? That is where the price economics comes in: the cost of cable, cost of design, and difficulty of synchronization. So getting to serial, suppose you now I think you understand what is the difference. Now we'll move on to why we are using serial communication most of the time, or at least most of the time in a substation. So the ultimate price is that serial can be clocked much faster than a parallel communication. To understand this, let us move to a whiteboard. So suppose we'll keep it simple. You're having a 4-bit data. You're the transmitter and you're having a 4-bit data. And the receiver is having a 4-bit register. Suppose you are using a parallel communication first of all. So you will have channels. I'm oversimplifying things here for your understanding. But basically you will be having 4 independent channels in a parallel communication. And these will be physical channels, means physical copper wires, or they might be traces in a PCB. So they are physical channels, and each channel will have a delay. So by delay, we delay in the channel is sometimes called electrical length of the channel, and each channel will be having a slight difference. So the mean, suppose this channel is having a 1 nanosecond delay, this channel is having a 1.1 nanosecond delay, and the third channel is having 1.2 nanosecond delay, and say for example for 0.9 nanosecond. So each channel is having a separate delay, and there is a net delay or an average delay of like say zero point 0.2 nanoseconds. So what ultimately happens is all your bits reach at a slightly different time. So this bit reaches first, then this bit reaches second, it reaches third, and this reaches at last. Because your delay is different, each bit reaches at a different time. Even though if you're sending at the same time, the receiver is receiving these bits at a different time. So ultimately the difference in your electrical length, or difference in the delay, or the differences between the channel is a limiting factor for your transmission speed. So the interconnecting cables or the channels is itself a limiting factor for your transmission speed. Whereas in a serial communication, they mostly use twisted pair. Most of the serial communication use some fashion of a twisted pair under the physical layer. It uses twisted pair, or it uses optical fiber, where you're only sending one bit at a time sequentially, and the delay does not affect, or the delay does not limit your transmission speed. In it limits actually, but it does not limit in the same fashion that it limits a parallel communication. For example, here, suppose you are sending a data every zero point 0.1 nanoseconds in this example. So what happens? Every zero point 0.1 nanoseconds, you are sending a new data. You're putting a new data on the line. You're putting some, so position to 0, you're putting a 1. So it takes 1 nanoseconds to reach, but you're sending it every zero point 0.1 nanoseconds. So what happens is, by the time the first bit has come, this channel is having a delay of 1 byte, because the delay between these two channels itself is comparable to the transmission speed. So the delay between these two channels itself is zero point 0.1 nanoseconds. So this channel will always be delayed by 1 byte. Sorry, this channel will always be delayed 1 bit behind this channel. So that is the limiting factor in a parallel communication. The speed at which you can send data is ultimately limited by the differences in the channel. And one more thing, because you're using a because you'll be using a clock to sample the data, and I'll explain this clock and sampling in the coming slides. So because you're clocking the data at the receiver end, there will be a clock skew. There will be a skew. By skew, what I mean, you're sending one clock, but you're receiving something different, and you're sending one clock to another circuit, and so both circuits will be getting different versions of the clock. Clock skew is happening because the clock is being sent in a physical wire, and the wire will have some attenuation. It will have some delay. So the clock what you're sending is not exactly received. And furthermore, you're sending it to two different places. Suppose you're having two receivers. Receiver one is receiving a one clock, and receiver two is receiving something else. So the difference in clock itself is a problem in parallel communication, because each of these channels will be sampled by a different. Suppose you're having eight channels, there will be eight samplers, and if each of the sampler is getting a different clock, they will be sampling at different times, and ultimately, you're in a parallel communication, that is a limiting factor. And you'll be having fewer cables in a serial communication. You'll be only having two pairs of twisted pair, but whereas in a parallel communication, you'll be having, if you're having sending 8 bits, you'll be having 8 channels. So in serial, you're having fewer channels and fewer cables, and in the interface or in the circuit board, this will give better isolation, and there will be less crosstalk. By crosstalk, what I mean is the data in one channel is affecting the data in other channel, or it is influencing by some electromagnetic phenomena. Whatever you're sending in one channel is getting affect is it is affecting the other channel. That is what crosstalk is. So the more channels you accommodate in your in your communication cable, the chances of crosstalk is more. But in a serial interface, you don't have crosstalk at all, because you're only sending one bit at a time. And furthermore, look at the design aspect. In a parallel interface, the electrical length of all the traces or all the channels has to be absolutely the same. You have to design for that. You will have, suppose you're sending 8 bits in parallel communication, you have 8 samplers. You will have 8 line drivers. You will have 8 channels. You will have 8 times the IC die area. You will have 8 times the PCB board area. And you have to design for the EST protection of all the 8 channels. But in a serial communication, all these things can be focused on in a single channel. So the design aspect is a little more easier. So you can use the extra resources to design for faster clock. So that is why serial interface can ultimately be clocked faster than a parallel interface. So even though the serial interface is slower, you can clock it faster, or you can make it run faster, and trade off. You can have that trade off with a parallel interface. One more thing to note is parallel works best over short distances or distances less than 1 meter. So parallel communication can be used in a uh, single circuit board, like a motherboard, or like a devices that are very close together, like a printer or a computer. So you can use parallel port when the devices are very close together, or when the devices are on the same circuit board. Then you can design the channel such that the channel length is the same. You can form a PCB trace, or you can form a circuit copper trace in a PCB board such that, the length of the trace is same for all the 8 bits. So this is possible to do when you are designing the entire system. You're designing the receiver, you're designing the transmitter, you're designing the channel. So that is when parallel interface is a feasible thing. But when you're designing to send the data over a long distance, like for example 10 meters to 15 meters, you cannot design for the attenuation or the delay or the clock skew. You cannot design for these factors. So that is when a serial interface is more preferable. Moving on to synchronous and asynchronous communication. So the fundamentally, you might have some idea about synchronous and asynchronous. Basically, what synchronous is you are having a clock in the transmitter end, and you are sending this clock as part of your data. Means you are having the same clock signal that the transmitter is using to sample the data at the receiver end. So what happens is the receiver will sample the data using the clock signal that you are sending along with the data. So you have to send the clock along with the data. That is the first thing. The receiver will use this clock to sample the data. So here I would like to explain what is sampling and what is clock first, so that you can better understand. This is to the whiteboard. So ultimately what happens is A clock is nothing but a sequence of pulses. So that is a clock. A clock is nothing but a sequence of pulses like this. And a clock can have variable length pulses also. Most probably it will have a same length pulses, but it might not, it is not mandatory. It can have any length needed. The length of the clock is not important. The edge of the clock is what is important in these communication digital devices. So the clock edge is important. Either it will sample your data in a rising edge, or it will sample the data in a falling edge. By rising edge, what I mean is the logical transition from a low logical low to a logical high. That is what is called a rising edge. So the clock edge is important rather than the absolute signal. So clearly you have to define when you are going to sample. Either you sample on the rising edge or you sample on the falling edge. You're sending the clock along with the data in a synchronous communication. So your data is also there. Some form of data is also there. You're having 1 0 1 1 0 0 1 0 0. So here, suppose in this case I'm using a falling edge, and each falling edge I'm taking a sample of what data you have sent. So that is why clock and sampling is important. In a falling edge, I'm taking a 1, here 0. So this is ultimately what data I receive. That is clock and data. This is data. So in a synchronous communication, what you're sending is you're sending the clock along with the data so that the receiver can sample at the appropriate time. Here, one more thing you need to note is that you can use a variable bit. Means you don't have to send it uniformly. You can use a variable clock frequency so that your data rate is also varying, and you both side has have the same clock because you're sending the clock along with the data. Whereas in a asynchronous communication, you're not sending the clock at all. You're only sending data, and both sides, the transmitter and the receiver, is having their own clock, which are not in sync, but which are having, they are set to the same frequency with minute differences between the frequency. Suppose you're setting your clock, transmitter clock as 1000 hertz. Your receiver clock is also 1000 hertz, but it will not be absolutely the same. There will be minute different, like 0.0001 hertz. It will be different, right? So that does not matter in a synchronous communication. That is what the point is. Your clock has to be absolutely close. It should not be like one is using 100 hertz, if the other one is using 200 hertz. That does not make sense. The clocks has to be set to the same frequency, so that even if there is a slight difference in frequency due to some design aspect, the asynchronous communication will adapt to that. But it is not like that both sender and receiver is using absolutely different frequency. They have to have an agreement, prior agreed upon frequency. And to synchronize the clock, at the start of the transmission they will use a start bit, and at the end of the transmission they are sending a stop bit. So the purpose of the start bit and the stop bit, here I am using the word start bit and stop bit, but I'll explain in more detail. It does not have to be a single bit, it can be a sequence of bits also. So more appropriately we can call it a start element and a stop element. So I'll send a sequence of bits. So the receiver will get alerted. Okay, he's starting to send something. So that is at what point the clock starts. And then I can send a few bits. And then if I send more bit, what happens? Both clock starts to drift away. So let me use the whiteboard here. Suppose this is asynchronous communication now, what I'm going to tell you. And the transmitter is having a clock, and the receiver is having also having a clock. The clock is very close to each other, but not absolutely the same. That is what is important. The clock is close to each other, but not the same. Let me take some clear example. Suppose clock duration for the transmitter is like say like 100 microseconds, and for the receiver the clock duration is say 101 microseconds. So now the rising edge. Let me say in this example, let me take the rising edge. So the receiver will sample at the rising edge of the clock, and this is the data set for example. Let's say this is the data. So what will happen? The rising edge of the first cycle, assuming that both the transmitter and the receiver is starting at the same time. They're starting at the same time. What happens is the first cycle will be in sync, and the second cycle, because the period of the clocks are slightly different, each period there will be a 1 millisecond phase difference. So the next cycle there will be a 2 millisecond phase difference. Because the frequencies are absolutely close together, each cycle will add a minute, it will be an aggregate. The error keeps on getting larger and larger after each pulse, or after each clock cycle. So after 3 clock cycles, there is a difference in mismatch between the rising edge of 3 milliseconds. Here, this is 3 milliseconds maybe. After four clock cycles, the difference is say 4 milliseconds. Because there is a fundamental difference between these both periods, the error just keeps on adding. So ultimately, so for example, in this example, after 100 cycles, after 100 clock cycles, what will be the difference? The difference will be 100 milliseconds, right? Because in each cycle you're having 1 millisecond difference. You can only use 100 cycles before the clock is absolutely out of phase. Like after this 100 cycle, maybe this clock is like this. After 100 cycle, maybe this clock is like absolutely out of phase. So but that doesn't matter, right? Because you're not using the 100 cycles. That is a beautiful fact in this asynchronous communication. The only fact, the only fact that you care about is that after you start the clock at the same time, there is x amount of clock cycles where they are in sync, right? That is the important fact. So even if there is a minute difference between these two clock cycles, for some x clock cycles, they are absolutely in sync. They are in sync, and this is just after starting. So that is what a asynchronous communication uses. You will send a start bit in your data so that the receiver can start the clock. The receiver starts the clock, and for some x cycles you can use this clock reliably. The more cycles you use this clock, the less reliable it becomes. So that is why there is a stop bit. You stop the clock at the stop bit, and in between the start bit and the stop bit is the actual data. So here if you do something, it can be reliably sampled by the receiver. By sampling, what I mean, I explained earlier, is the actual measurement of the data. That is what is sampling. So using a start bit, you can overcome the fact that you're not sending a clock at all. You are having a agreed upon frequency prior to sending the data. Even though the frequency is slightly mismatching because of design aspects, the fact that you're sending a start bit and using the start bit to synchronize the clock in advance, you can use this clock reliably for a particular x clock cycles, and after this x clock cycles you stop using the clock, you stop the transmission and you start fresh. You start sending another start bit, and then you start again. You reset the clock and start again. That is what an asynchronous communication is. In asynchronous communication, you have a start element denoting the start of a clock. It is used to align the phase at the beginning of the transmitted word, and then you're sending X bits or X amount of data. And then you're stopping the transmission, and then you're sending it again. So this is asynchronous communication. And examples of asynchronous communication are RS-232, RS-485 UART, and examples of synchronous communication are this SPI, serial peripheral interface, and I2C. I2C is in the integrated circuit. So these are synchronous communication used when you need to send whatever you need to send is uneven, means the data is not coming at a fixed rate. So you have to send the clock along with the data so that you can synchronize at both ends. But whereas in a asynchronous communication, you have to have a predefined frequency and a predefined start bit. You need to have a predefined sequence of stop element. You need to have a predefined number of bits where you're sending in between. So all these things needs to be predefined in an asynchronous communication. You can also use asynchronous communication without the start element or the stop element, but in that case also there will be some way to recover the clock from the data. That is the basic thing with asynchronous communication, is that there is always a way to recover the data from the recover the clock, sorry, recover the clock from the data. So you don't have to send a clock separately. The clock can be recovered from the data, it can be recreated from the data, whereas in a synchronous communication you are sending the clock with the data. That is a basic difference. So in this slide you can see you're detecting a start bit here, and the clock is getting synced. It is getting sampled at the clock signal, and then there's a stop bit. You're stopping the synchronization, and your clock timer, you're using a timer or a clock, it stops. So moving on. So in the coming modules, when we'll discuss about protocols and standards. So you have to get this clear first. What is a protocol? What is a standard? We use the words interchangeably. Okay, that is a protocol. What is a standard? You're always using these words interchangeably, but there is a distinction. The distinction is that a protocol has a specific purpose. Protocol has a specific purpose in that it is limited to how the data is exchanged. It does not care about the safety, it does not care about the performance, or it does not care about security, system design. The scope of protocol is limited to a logical construct that both the sending and receiver party uses, so that they both understand each other. The scope is purely limited to how data is sent, how data is received, and how data is processed. So abstract logic is defined like these many start bits I should use, these many stop bits I should use. This is the way I should encode the data. This is the way I should scramble the data, or this is the frame that I use. This is the particular data length that I use. These are logical parameters that are fixed, and this is what a protocol defines. It defines what is the software underlying software, or it defines the underlying logic message structure needed at both ends. Whereas a standard has a broader scope. A standard is like it is like a committee that sits together. A committee consists of industrial experts, maybe regulatory organizations, or maybe some OEM manufacturers who comes together and say that we are we are all manufacturing devices, so the devices needs to have some safety standards. We are having some safety design constraints. We are having some performance constraints, and the devices need to operate with each other. So we are having some standards that everyone will follow, so that all these constraints are met. That is what a standard is. Standard is having a broader scope. It is not just limited to the fact that these devices need to communicate with each other. It has a broader scope that the device needs to perform like X and Y. The devices of different manufacturers needs to interoperate with each other. That is why a standard is always having a broader scope. A standard can define, or it can use an already existing protocol. It can define a new protocol. So the standard is like a superset, and the protocol is like a subset. And some examples of standards and protocols are like, we are using Wi-Fi. So the Wi-Fi standard is IEEE 802.11, which which mentions how much power you can transmit, and what is the spectrum that you have to use, what are the performance criteria that you have to meet. So that is what a standard is, and the WPA is is a protocol. The Wi-Fi protector access it is a authentication protocol. Means logging in, when you're logging into a Wi-Fi, you use a WPA. So that is a part of a protocol that you use when you log in to a Wi-Fi device. So the protocol is defined, is the scope of the protocol is limited to the communication aspect, whereas a standard has all take care of all the physical, all the design and all the safety aspects as well. So that is what is the difference is. So basically in this module, what you're seeing, we are seeing the difference between serial and parallel. We are seeing the difference between synchronous and asynchronous, and we have seen a start bit, why start bit is being used. We have seen why a stop bit is being used, and all these things. We have also learned the difference between a protocol and a standard. Keep in mind that a standard can, may, and shall define a protocol, whereas a protocol is an independent entity. So that is what you have to take away from this module. Thank you.